Yay, there we go. Do, do, do. Do, do, do. Hi, everybody. This is the Chem 161 review session. I'll keep going as long as you all have questions. So, we'll be hearing that music, the interstitial music, a few times today. Once I answer all the questions, I'll put it back up and you can just ask more questions. And then if I don't get anything else, then we'll call it a day. So you're allowed to ask any question about any content from the quarter at all, whether it showed up on a quiz, exam, homework, lab, etc. Because the purpose is to study for the final. And my tablet does work. I forgot to check it, so I'm glad that it's working. Okay, so the first question that somebody had was related to bonding types in terms of resonance structures. Let me move this actually so I can see the chat. And then another question was asked about Lewis structures and shapes. So we can sort of do both of those at the same time here. Now, I don't know if you have specific questions that you want to look at, but I'm just going to make up examples here that I think will answer the question here that is asked. So I'm going to start carbonate, and the number of Lewis or the number of resonance structures that carbonate can form is probably relevant to what we're asking here, because that'll influence, like, is it bond and a half, or is it 3/4, or whatever. So let's count the number of electrons. So we know that each carbon is 4, each oxygen is 6, and there are 3 oxygens, and then I have this extra pair of electrons that is added in here. And so that means I have 24 electrons. And so when I draw my resonance structure, I got a carbon and then oxygens. I'm going to just put the oxygens around it like this. And that will be 2, 4, 6 electrons. And I'll just go around the sides here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that was all of my electrons. I don't have anything left to put on the central atom, so now I got to make multiple bonds. So I'm going to do this. We're going to put a multiple bond here. Now this is an ion, so we'll do that. And so there's my Lewis structure for carbonate. But I could have drawn a resonance structure where instead of putting the double bond in the top position, I could have put it down here, right? And then I could also have done the same thing where I instead put it down in the bottom left position. And then I get this structure right here. I have no idea if that actually fits. Yeah, it did fit on the thing. I'm right up against the edge of the drawable space here. There we go. So here are my structures. And so these are resonance structures because all my atoms are connected in the same way, but I'm shifting around where the double bond is. So you could kind of think of a resonance structure as moving electrons. So if I move this pair of electrons into the double bond position, and then I take this pair of electrons and I move it back here, that will get me to the second structure. And then I could put this pair of electrons in the double bond and move this back here. That'll get me to the next structure. And then to go all the way back to the first structure, I could just move this guy back to where it was and this one in here. So in each of these cases, I'm moving a pair of electrons into a bond and I'm moving another pair of electrons out of a bond. So you're going to look at a structure diagram like this in organic chemistry. These are called electron mechanisms. And really, they just show you where the electrons are going. So all resonance structures follow this sort of pattern of, oh, I'll just move the double bond around, and here's how. Now, if I look at a given position, I'm going to pick this position right here. For a molecule, I can calculate what's called the bond order. And this tells you, oh, is it mostly like a single bond? Is it mostly like a double bond? What's going on here? And the way that you calculate that is, remember, number of bonds in the selected position divided by number of resonance structures. So for carbonate here, I would have 1, 2, 3, 4 bonds over 3 structures. And so we would say that the bond length and strength between these two atoms would be similar to that of a 4/3 bond. So a little stronger than a single bond, but not quite as strong as a double bond. Because it's 4/3, it's 1 1/3. Will the exam include the cheeky history questions? I'm pretty sure that those show up. I think I might have modified them slightly. I make no guarantees that they will or will not be cheeky. So let me do another one of these. Let's do... Trying to think of one that would have multiple bonds in it around the central atom. I'm not really coming up with any, unfortunately, other than just like... Because the problem that I get into is if I do something like this, there are so many resonance structures that it becomes impossible to ask the question. So we could just do nitrate, I guess. Nitrate is actually the exact same thing as this one above. Like, just replace C with N. That's what we get. I could do nitrite. We'll do that. Will the history questions be different than the ones on the Chapter 2 test? I don't actually know. I would have to go look it up. I don't know off the top of my head, though. Alright, so number of electrons in nitrite here. 12, 17, 18. And if I draw my... We'll just draw it like this for now. 2, 4, 6, 8, 10, 12, 14, 16, 18. And so I do need a double bond. And I could make a resonance structure like this. What am I doing? There we go. So there are my resonance structures. I've moved this double bond over to the other side by shuffling our electrons around. And if I wanted to calculate the bond order in a given position, I'm going to pick this position. Just why not? then I would get 1, 2, 3 bonds over 2 structures. And so this would be equivalent to a 3 halves bond. Now, if you choose a different position, you'll get the same result every time. I don't know how you would calculate Z effective for a molecule. Z effective would be for an atom or an ion. Let me go up and make sure I'm not skipping anything here. So I do want to go over shapes real quick while we're on these molecules here. So if I go up to this one right here, and I count the number of electron groups around the central atom. Actually, this screen is kind of full of drawing. So did I draw on a different layer? Yes, there will be sigma and pi on the exam. Which one you get is totally randomized. No, I cannot make it smaller. So I gotta actually get rid of this. So we'll draw carbonate over again. So regardless of which Lewis structure I have for carbonate, so I could do this with any of the resonance structures. But when you do electron geometry, so and I teach out of so many textbooks that I don't remember what yours calls it. So the electron geometry or Vesper geometry is the number of electron groups around the central atom. Remember that an electron group is either some number of bonds between atoms or an electron pair that is non-bonding. So again, what that means is that either a single or a double bond would be an electron group. So on this carbonate right here, around the central atom, so C is my central atom, I have 1 electron group, 2 electron groups, 3 electron groups. And now that you've seen chapter 5, you can understand why we count a double bond as 1 electron group, because the sigma bond is the electron density directly between the atoms, and then the pi bond is parallel to it, going around it. So it occupies the same physical space in terms of its orientation around the central atom. So in this case, we have 3 electron groups. And of those 3 that I have circled, none of them are non-bonding electron pairs. So what we do now is we go to that geometry table, which was on a previous slide, and hopefully you have that bookmarked or saved or something. I know that there's a copy of it in the Discord, so. And you just look up the shape. So for 3 electron groups, the Vesper geometry would be trigonal planar. And then of those 3, 0 of them are electron pairs. So that tells us the molecular geometry which depends on the number of electron pairs that are non-bonding. So the molecular geometry for this, since there are 0 electron pairs, it's the same. Now, if I go down here to NO2 and I look at its geometry, we could do the same thing. Let me erase this real quick. Ooh. Did I make a new layer? No. My eraser just doesn't do anything. Oh, I know why. I gotta do this. There we go. Alright. I just read your analogy, and I don't know if that is, I'm not sure of the adjective to use for that. Like, should I be concerned about you after this class? So we're going to do more complex examples that for geometry here, but like in this instance right here, I'll circle the electron groups. So I got 1, 2, 3. So it's Vesper or electron geometry. I don't remember which term we use here. Would still be trigonal planar. I really wish that every textbook called it the same thing. And then the molecular geometry of these 3 electron groups. So we have 3 groups, and then 1 is a pair of electrons. That's this right here. So we go look up the shape for 3 groups, but 1 is an electron pair, and you get bent for that. And yeah, you can look up the answer on Google. Just make sure that you're getting the right answer. There are mistakes out there. Like, if you type in certain molecules, you will get every Lewis structure under the sun. And if you want to gamble on which one do you see the most, it's up to you, but you guys are undergraduates, you realize, right? It's a self-deprecating humor. All right, so what we'll do here is let's do your molecule here. So let's do SEF5. I've immediately hit an issue because there is an odd number of electrons in SEF5. So I'm going to assume that this is what you meant. Let's see here. 7 times 5 plus 1. All right, so this has 42 electrons around it. So selenium goes in the middle. And then I'm just going to put F's all over the place. So 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So that's 30. So I have 2 left. There we go. So there's my structure. I don't need to make double bonds because everything has an octet. But now let's look at the geometry. So I need to circle all the electron groups around the central atom. So the central atom is selenium here. So I got 1, 2, 3, 4, 5, 6. So because there are 6 groups, that would make it octahedral Vesper geometry. Now, of those 6 groups, one of them is an electron pair. So we have to go look at what member of the octahedral family had 1 electron pair in there. And so that was square pyramidal. And so what that means is that if I were to draw like a square base pyramid, so there's my square base pyramid. I'm going to go like this to make it look more 3D. There we go. If I were to put all of the atoms in this pyramid, so selenium would be in the base, fluorine, 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 and then the electron pair would be below it. Like that. I'd prefer to keep these two review questions. But if we get to a point where there's nothing going on, like I can talk about it. It's just that I'm not going to test you on the lab stuff tomorrow. Well, kind of, sort of, I'm going to test you. The questions are a lot easier. Let me see here. The text is going so fast that I just want to make sure that I'm hitting what I want here. How do we do the electron configuration of ions? We definitely do that. Let me leave this right here for now. All right. I know this is a common mistake that a lot of people made. So remember that if you have an electron configuration for an ion, and the ion is negative, then what you do is first write it out for the neutral atom. So that would be this. And then I have to account for this ion. So this is an extra electron. Oops. So I just increase this guy. And you're all set. Now, for something like copper, I would do the same thing. So argon, 4s2, 3d, I think it's 9. Because this is going to change to my exception here. So remember that if you land on d9, steal an electron from the s orbital to make it d10. And then when I remove these electrons because of the +2 charge, you always remove the valence electrons first. So I need to remove 2, so the 2 that go away are this one and this one. So copper 2+ will be argon 3d9. Okay? If you take them away from the d electrons before you take them away from the s electrons, then you'll get the wrong answer, because 4s1 3d8 is not correct. So be careful. Remember that when you are adding electrons, you just tack them on there. Like you normally would for anything with extra electrons. Just throw them in the electron configuration. But if you have a cation and you're taking away electrons, you have to take them out of the valence shell first. Because on average, the valence electrons are the furthest from the nucleus. And so they're the easiest ones to ionize when they are furthest away. Even though you get some weird effects of energy and distance at that point. Let me see here. It looks like the ionization energy question was answered. If you have other questions, let me know. Here we are kidnapping people. Is it safe to write the electric config for cobalt in copper's case and fluorine in oxygen's case? For fluorine in oxygen's case, yes. For cobalt, no. Because make sure that you Oh, and you said that down here. Yeah. So when you're removing stuff, you're always going to be taking away those s electrons first. So you're not going to end up with the same number of electrons as other things. Going backwards, anyway. And so this only happens in the transition metals section or in the lanthanides section, which we're never going to deal with because who cares about lanthanides? So if I give you any element in the transition metals and then I take away electrons, you get rid of the s electrons first. Because you always do valence. Remember that valence is the highest number n. So there's a blurb in your textbook that says you get rid of S, then D, then F, or whatever. I don't know. It's really stupid. And the whole point of me saying, okay, valence electrons are just highest level n is so that it works. So strip away all of the valence electrons first, and then go down to the next level, and then just work backwards. You're never going to see an ion that's like minus 22 electrons or whatever, and have to go all the way digging into the core. So, can we also do iron 3? Yeah, sure. So, for iron 3, if you want the Discord link, it should be in the announcements. That was way at the start of the quarter, though. So you'll have to do some digging. So let's see here. Sorry, I'm looking up at the questions here. I don't think I answered this question right here. So, does the -1 charge come from the lone pair? For our structure, the -1 charge is just there so you have an even number of electrons. So, odd-numbered electron species don't really form very often. Instead, what they do is they react with something and take or give away an electron. So for iron 3 here, so we would do... I actually have my periodic table at this time. So 1, 2, 3, 4, 5, 6. So there's just regular old iron. And so I need to remove 3 electrons, right? So lose 3 electrons. So I'm going to get rid of these 2 first. Actually, let me do that in a different color. So these 2 go away, and then this changes. And so you should get argon 3d5 for that. And then for sodium with a -3... Oops, I forgot my -3. There we go. We would write the regular electron configuration, which I'm not going to do neon. I'll just do it this way. So there's the original electron configuration for sodium. Now I got to add 3. And so I'll just add them here. Well, I can add 1 like that. Actually, hold on again. Different colors. So there we go. I can do that, and then I have to add 2 more, so I would do this. When you're adding in electrons, you just fill them in the order of the alphabet principle. So after 3s would be 3p, then 4s, then 3d, and so on and so forth. Actually, you know what I can do? Hold on. Did somebody just join in? Yeah, it looks like you did. Okay, cool. I realized I could just go make an invite link on the Discord, but it looks like we already got it. Yeah, that's what I figured you were trying to do, because I can't actually give you permission to post it. All I can do is put you in timeout, which, no, I'm not going to do that. Maybe I should for suggesting that we kidnap small children as an analogy, although I've suggested that, so. I don't like children, if it isn't clear. Children love me, but I don't get along with children. What else do we have here? Oh, naming stuff. Okay. Yeah, we could do that. That was like way at the beginning. I'm sorry, I forgot all about that. Sorry, I want to make sure that I am getting all of the questions in here. How does adding a spin affect the periodic table? I'm not sure what you mean by adding spin. So, spin is a property that all electrons have because it's a property that anything in motion has. Like if you have a ball and you try and roll the ball perfectly straight in a frictionless environment, it will start just spinning in all directions. You can see this when you're bowling, like when you throw a bowling ball. The ball will spin in all sorts of different orientations, even though it's moving along a trajectory. Oh, I see. Okay, yeah, we can definitely talk about that. Okay. Yeah, so if there were multiple spins available, then what would happen is the following. So, yeah, you guys are digging into my special question. So, when we draw the electron configuration diagram, it looks something like this, right? And what we said was that the max number of electrons in an orbital is 2, right? And the reason for that is because here's my orbital. I can have spin up and spin down. So, and this is the Pauli exclusion principle. And that is no orbital can contain electrons with the same spin. So if I have 3 spins available, or so if I have 2 spins available, plus 1/2 and minus 1/2, then I'm allowed to put them both in an orbital. So up is spin plus 1/2, and down is spin negative 1/2. But now let's suppose that you discover in like a distant, faraway galaxy or universe or something like that, there's another spin. And so what that means is that in that environment, all the electron configurations would change if the Pauli exclusion principle was still valid. And so my electron configurations would now look like this. When I'm filling in stuff, right? So if there are 3 different spins, now you can put 3 electrons per orbital. And so the periodic table would compact a lot. Well, it wouldn't compact actually. It would there would be an extra amount of elements in the P section and S section. There'd be fewer periods basically. So the element that filled in say the 2p orbital completely would be 1 2 3 4 5 6 7 8 9 10 11 12, whatever the 15th element is, which means that phosphorus in this alternative galaxy or universe or whatever would be a noble gas if there were 3 spins. Why doesn't each orbital need 6 electrons? Well, you only need 2 because there are just 2 spins. There's up and down. Or do you mean in this special case? In this case, you would need for all your s orbitals, you would need 3 instead of 2. And then for all your p orbitals, you would need 9 instead of 6. And then for all your d orbitals, you would need 15 instead of 10. So it's basically each time you have a box for an orbital, you would add an extra electron. And then all the rest of the stuff stays the same because the rules for where electrons can be hasn't been affected by spin. We definitely talk about sigma and pi. So remember that a sigma bond is, so if I have two atoms like this, and they orbit, or their orbitals overlap like so, along the internuclear axis. So here's where my bonding electrons would be. This would be a sigma bond. I hear you, but I don't see you. Where's the cat? Maya! Maya wanted to say hi one last time. Where are you? I don't know. Oh well. Okay. So, what types of bonds will make sigma bonds? So this could be an s and a p orbital, or hybridized orbitals. Because we don't really use s and p orbitals by themselves. Where are you? I keep hearing you. Where are you? There you are. Let me get Maya real quick. Maya, say hi. Say hi. Say hi. Hi. That's her happy chirp. Now, if you have two atoms that are like this, and you have p orbitals that are side by side. Wow, I really made that one out of shape. Let's try that again. Let me actually put these closer together. So there's my p orbital, and there's a p orbital. And you can see that where they overlap is over here. Oops, I don't actually want to put 2 electrons down there. That's okay. So a pi bond is parallel to the internuclear axis. So this is what those bonds are. So sigma bonds go through the line that you draw between nuclei. So these big dark dots that we've drawn are our nuclei. A pi bond goes parallel to it. So what that means is that if I'm looking at electron density, I can either go between the nuclei or I can go around it. The first bond always goes between. So the first bond, and I suspect this is the information that you want here. So the first bond is always sigma. And then the second and third bonds, well, the position between the nuclei has already been taken. So you can't put another bond there. But you can put bonds around it, and so they're pi. So, for instance, if I had this ion here, and I drew its Lewis structure, and I got this. So, there's my molecule. The first bond that I draw is sigma. And then the other two bonds that I draw, which would be this one and this one, these are both pi. You already said hi. Do you want to say hi again? Want to say hi? Say hi. Are you shy? Say hi. Now she's shy? I don't know. Oh, she wants to jump in my lap. Well, I can't do that. Not right now. You can't jump up here. So that's how you do sigma and pi. So if you were looking at a giant molecule, like say, hold on, let me go get one that we can draw on. So let's see here. Here's an easy molecule to look at that I know has double bonds in it. So copy image. Let me do that real quick. Paste. Yeah, it didn't work, unfortunately. So, sorry, give me a second, and I will download this molecule. So save image as. We'll just throw this in the work folder. Show in folder and Photoshop. There we go. How do I make this drawable? I just hit enter. Yeah, there we go. Okay. Oh, I have to rasterize it. There we go. Boop. There we go. That took some effort to get. So, this is the structure of caffeine. And so, I need to actually amend this structure a little bit. So, first thing I'm going to do is I'm going to put in all the electrons that you wouldn't be aware were there. And then I'm going to do this. Because that's what these are. You guys don't know what organic nomenclature is. And, oh, I got two more here. Okay. That should be the molecule. Is caffeine explosive? Only if you drink too much of it. So now what you would do is, for example, maybe this question asks you, count the number of sigma and pi bonds. And so what I would do, if I were doing this type of problem, and I had a picture of the molecule, I would do this. I'd go 1, 2, 3, 4, and I just start painting one bond between each thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So there are 24 sigma bonds in this molecule, presuming that I haven't missed a connection here. And then I can do the pi bonds because that's everything else that's left. So 1, 2, 3, 4. A lovely sea green there. So there you go. That's how you count sigma and pi bonds. Now, if we really wanted to have some good questions about this, I could point at any atom on this structure and ask what the geometry is around it. And you would be able to do that pretty easily because you could count electron groups. So, like, for instance, if I chose... I'm trying to get a unique color here, but I've sort of used them all, haven't I? So let's suppose that I looked at this nitrogen right here, and I said, what's its geometry? Well, you could say, okay, there's 1, 2, 3, 4 electron groups. So 4 electron groups is tetrahedral. And because one of them is an electron pair, that would make it trigonal pyramidal. So you can do stuff like that too. In organic chemistry, you pretty much only go up to 4 because organic chemistry only uses the top row elements anyway for like 99% of it. Organic chemistry is just all the crazy shit you can do with carbon and oxygen and nitrogen and hydrogen, really. And there's a lot of crazy shit, it turns out. But because you're only using top row elements, then you really only go to 4 electron groups. So that's the geometries that you're going to be seeing the most, is linear, trigonal planar, and tetrahedral. What other questions do we have here? I might have gotten everything here. I don't even know where the, Oh, yeah, here we go. So, determine the wavelength of a photon in nanometers that's emitted from a hydrogen atom. So, yeah, we can definitely... Oh, I keep forgetting your acids. I'm sorry. Let's do the acids first, because I'm thinking about that. Okay, so how do you name acids here? Oh, I gotta make the pen nub the correct size again. So, naming acids, there are 3 mechanisms to use. And so, we have these 2. Which are easy to define. So, if something ends in H, the naming scheme for it is blank ic acid. And then if it ends in ite, it's blank us acid. But there's really just one more. And so this is for binary acids, so like chloride or not hydroxide, chloride, bromide, iodide, etc. And so that's the pattern. So when is hydro used or not used? When the ion you're working with ends in ide. So for example, if you had HCl, then the ion that this is right here, when you split this up, this is chloride, right? And so because it ends in chloride, it has ide here, you would just take this. Let me go to the next layer here. You just take this part and then put it up here. So HCl would be a hydrochloric acid. Now, if I did that with something else, so like, say, HNO2. So I have H plus and NO2 minus, which is nitrite. So this ends in ite. So I just take the rest of it and just throw it right here. There you go. So that's how you name acids, is you just have to look at the ion that is associated with the H. You just chuck out the H's. You don't care about them. And then name the ion that's there. If it's polyatomic, you'll have to look up the name if you haven't memorized it. I mean, it's an online class, so you haven't memorized it. Go look it up. Yeah, use Lentech if you're going to do molar mass. You can use Wolfram Alpha for pretty much anything else. However, I suspect that Wolfram Alpha is more for engineering than it is for chemistry, so some of the data on there might lean towards physics. Which, I mean, chemistry is just applied physics, right? So it should mostly be alright, but there are some things that we do that physicists don't, and vice versa. So what else do we have here? Oh, I was gonna do one more Rydberg equation thing before I called it for a break. So someone asked about the Rydberg equation. So first you need the Rydberg formula. So that is 1 over lambda equals Rydberg constant times I'm doing this from memory. I hope that that's right. And then RH. I want to say that it's like this. I don't know if that's right, though. Let me look that up. Rydberg constant for hydrogen is... Apparently it's changed. How many digits do we? 3, 6, 7. So 1.0973 is what they have listed here. Oh, no, down here. 1.09678. Which is what I have. Okay, cool. Calculate from the reduced mass of the electron. I don't actually know what they're talking about there. Okay, so this is the right number. And so what we want is for an electron in hydrogen. So we'll say n equals 1, n equals 2, n equals 3, n equals 4. And I have no idea which transition you wanted, so I'm going to just pick this one. So I'm going to start at n equals 4, and we're going to drop down to n equals 3. So in order for this to give me a positive number, the smaller number's got to go first. So n1 will be 3, and n2 will be 4. And so I can calculate that by saying 1 over lambda oh, oops, hold on. Times 1 over 3 squared minus 1 over 4 squared. And so I can calculate this. And before I do that, I want to see if I could find this. Oh, man, I don't know if I can find this on... Let's see here. Oh, this might be it. Okay. So let me see if I can... I found this the other day, and I thought it was stupidly cool. So let's see here. So, boop. I know a lot of people have trouble typing this in their screen. So now the chat is a calculator. So if we want to calculate this number, I could just do this. Boop, boop, boop. So 96776 times 10 to the 7. We're going to multiply that by... So I want 1 over 3 squared. So there's two ways to do this. So you could do this. 1 over 3 squared. But that's kind of cumbersome to do, so this is what I do instead. There. That's 1 over 3 squared. Minus 1 over 4 squared. And then enter. So this is 1 over lambda. 533,155. Per meter. And then what I can do is, well, I don't want 1 over lambda, I want lambda, so I'm just going to take my answer and raise it to the -1. And so that would be my answer in meters. So lambda is just, if we do this, we get 0. Well, you know what, this is silly. There you go. 1.875. I don't know how many sig figs we get. I don't care about sig figs for this. So that's that many meters, which I could then convert to nanometers because in a meter there are 10 to the, or in a nanometer there are 10 to the -9 meters. So I can do this. And there's your, oops, that's, I know what I did. Hold on. -6, so there's that. Oops, not times. There you go. So this would have a wavelength of 1875.6 nanometers. There you go. And if I asked you, like, what type of photon is this? Well, this would be IR. Because its wavelength is too big to be visible. So that's how you use the Rydberg equation with a calculator. I wish I could show you where I got this from, but I have no idea because it doesn't reliably work when I click on this link. As far as I can tell, I am in a testing site for like an elementary school in North Carolina. I mean, it's Google. That's, yeah. Harris Road Middle School is what it says. Oh, you could kind of see that because the calculator's on this page, but they have access to a TI-30 online, and I was just like, wow, this is really good. So if I could just download this page and have it, then I could have a calculator on screen to show people, which I think is super cool and also super helpful. Now, the reason that I like that one specifically is because it actually is a TI-30, and a lot of people actually have TI-30s on them. So what I am typing in is literally what you would type into. In fact, I had a student take a picture of her calculator and send it to me for a different class where I didn't use this calculator to do that. And I was like, oh, I know exactly what to do because you have the same calculator. So I was able to diagnose that. But yeah, as long as this link works, like, I'll just keep using it. So. Okay, so we've definitely gone over. What I'm going to do is I'm going to put the music back on for a few minutes here. If you have other questions that I have not answered yet, like, I think I see a few in there, but like, please repeat them if there's anything that you want me to go over. But we'll definitely take a 10-minute break. Type anything at the bottom of the chat that you would like me to go over when we come back, and then I will be more than happy to do that. Where's my timer here? Normal timer. There we go. So we'll do this, and then I'll start the obnoxious repeating music again, and I'll see you in a bit. Do do do. Do do do. All right. So there was a question about an empirical formula. So I had to actually go grab one. So that'll take me just a second here. Let me grab the textbook. So empirical formula would be chapter 6, I think. So table of contents. Yeah, here we go. So let me just get the... Oh my goodness, go away. I'm just trying to get this pop-up off of my screen from the textbook. There we go. Okay. So we could do this question. So empirical formula of hematite. So hematite is a mineral that contains both iron and oxygen, according to your textbook. And the sample of hematite that they have is 34.97 grams of iron in the hematite and 15.03 grams of oxygen. And so to find any empirical formula, the first thing you gotta do is turn everything into moles. So if I turn grams into moles here, in a mole of iron, according to the periodic table, there are 55.85 grams of iron. So how many moles is that? 34.97 over 55.85. So I have that many moles of iron. And then for oxygen, I'll do the same thing. We'll turn grams into moles. So there's the number of moles of each of the substances in my sample. So once I've got these two things together, I can make the pseudo formula. And then I'll divide by the smallest number, which was this. So once I've done this, I will then know the ratio of iron to oxygen, with iron being 1. So iron is just 1 here, and then oxygen would be 0.9394 over 0.6261, which I suspect is going to be 1.5, and it totally is. Now, you can't have fractions, so we have to multiply by 2 to remove the fraction. Now, when you do empirical formulas, sometimes you land on decimals because your empirical formula doesn't actually have a 1 in it. So in this case, this is the empirical formula. The simplest ratio of the elements is 2 to 3. And if I reduce that further, then it ends up being 1 to 1.5, but you can't actually have half an oxygen, right? So, turns out hematite, which is a lovely black mineral, when polished, is just another way that rust is formed under high pressure conditions. So that's an example of how to do an empirical formula problem. Is just, well, we can summarize over here. So For an empirical formula, convert your samples to moles. Then write the pseudo. And you can do that with any practice problem that we do. Just turn it all to moles, make the pseudo formula, make the empirical formula. All right. There weren't other questions in the chat, I don't think. If you want to see other examples of stuff, let me know. I think we answered the Roman numerals question. For Roman numerals are required for anything that has a variable charge, and the things that are not variable, so the things that are fixed, are anything in groups 1 or 2, and then aluminum. And then depending on the text that you're using, there are other elements that are included, such as, excuse me, cadmium and silver and gallium and stuff like that, but I don't make you learn those. I honestly think we should just apply the Roman numerals to absolutely everything, rather than have all these weird exceptions, but that is not, unfortunately, what we do. Alright, so I think that might be everything that has been asked, so what I'm going to do is I'm going to put the music back on. I'm just going to leave it playing for like 5 more minutes, and then if there are no more questions, we'll call it a day. So, we'll just go like this, and then here it is again. Oh no! It's so catchy! Alright, I'll be back in 5 minutes. Let me know if you have anything else you want me to go over. Alright, so it looks like we don't have any more questions here. So I am going to call it a day. I'm not going to be around very much today because I have other classes to do review sessions for, but if you drop any questions in the Discord, I will be around later to answer them. Email also works too. Tomorrow, I absolutely can't answer anything because it's the final exam, other than, hey, the final isn't working. Like, that would be a question I would immediately answer. But I can't answer any content tomorrow, so if you have anything for me, today's the last day to do it. Make sure you get all your stuff in by any deadlines that I've posted. So lab worksheet number 5, due today. Last call is tomorrow. You can NQA it, but all NQA needs to be in by Friday. I sent out an announcement for that because I'm going to have everything that I need to grade over the weekend is due for me Tuesday. So I have a deadline. My last call is Tuesday at noon. If I don't have grades in by then they get very, very upset. So please make sure you turn in everything by the deadline. And thanks for a wonderful quarter. It's been great. You guys have been terrific. Out of my classes this quarter, you guys have been the most active by far. I suspect that that's because there are just more of you, and so it's easier to get the ball rolling. But I really appreciate everybody, like, being engaged in the chat and also in the Discord and making a community. So I hope that sticks with you through the rest of college. So keep those friendships and keep those connections. And thanks for putting up with me, basically. Thanks for tolerating me in all of this. So, all right, have a wonderful rest of your day. Good luck on the finals, and best of luck to you beyond this course. Take care.